I'm Stefan. Topic of my talk is stochastic graph feed modeling for cross-modal connectivity estimation. Okay, as you can see here, this is a model that we previously introduced. The main idea of the model is that we have these nodes, and that activity at those nodes spreads through a connectivity structure to other nodes. So specifically, we model electroencephalography data here, so electric activity on brain regions that are connected by a network. Yeah, so this model is given by the equation here on the by this equation here over there. The important part here is this Laplacian matrix that encodes the connectivity structure. And if we solve for this Laplacian matrix, we get, with some approximations, the equation here at the bottom. And essentially now we have a way to compute the connectivity structure just from the data that we measure. So we were interested in whether the connectivity structure that we get from electroencephalography data is sort of similar to the one we get from fMRI data. Like, do we estimate some sort of modality-independent connectivity structure? And to answer that question, we used two data sets. They're both simultaneous fMRI EEG data sets. In the fMRI data set, we had to sort of locate the position of the EEG sensors and then compute the connectivity between those regions. And as our metric, we then ask, okay, how much is the EEG and the fMRI connectivity aligned? So it's just the correlation here that we're using between the entries of the adjacency matrix. Okay, these are our results. The table and the figures here show the same thing. We have basically three versions of this heat model techniques, and you can see the blue one is sort of on both data sets performs the best and gets the best sort of cross-modal connectivity, even though the correlation is not very high. But at least one thing we see here in this data set is that it's above 0 for almost all patients. Yeah. The other good thing is that it's actually a very fast measure because we can directly compute it if we have the data. So it's a fast connectivity estimation. Okay. So this is my last slide. So there's some applications that we're thinking of with this technique. It could be really useful for graph-based techniques such as graph signal processing or graph neural networks, because the graphs here play actually a central role, and it's often not clear how to determine this graph. And if we have a model-based technique, then it makes it easier to interpret the results of graph neural networks, for example. And with this, I'd like to thank you.
Thank you so much, Stefan.